Next exercise number 10. If every prime that divides the positive integer n also divides the positive integer m, then we have to establish that the phi value of nm equals n times the phi value of n. In particular, this means that phi of n squared is equal to n times phi of n, because every prime divisor of n obviously divides n. We start the solution like this. The result is trivial if m is equal to 1, since in this case n is also equal to 1 because of the given condition. And if both m and n are 1, then nm is 1, so this side is 1 and this side is also 1. And the result is also trivial if n is equal to 1 irrespective of m. No matter what m is, if n is 1, then both sides equals phi of n. So we now assume that both n and m are greater than 1. Now because n and m are both greater than 1, by the fundamental theorem of arithmetic, each one of them will have a prime factorization. And let their prime factorizations be these respectively. What was the condition given? The condition given in the question is that all the primes that divide n also divide m. So these primes which divide m, we are assuming of course that the exponents are all positive integers. So each of these p's divides n, so all of them should also be present in m. That means here these exponents, the s's, s1, s2 up to sr, these are also positive integers. But m may have some other primes also. So this other part where these q's are also primes, it may be there, it may not be there. Okay. But if it is there, then the exponents are again positive integers. Then obviously the prime factorization of nm will be this, where you just multiply these two expressions. So here you are getting ki plus si as the exponent of pi. The rest, this part is the same. And now we concentrate phi of nm, which of course by formula is this. You write the number nm and then you multiply by this type of factors. This calculation is to be understood like this. If this part is present, then these factors are present, otherwise they are not present. Then in the next step, we segregate this entire thing into two parts. We keep these powers of p's, where the exponents are k's, together and write the rest separately. And finally, then you notice that this is nothing but n, of course this is n, and this part is phi of n. So that's how you get n times phi of n as phi of nm. Next, let's see number 12, where a positive integer n and its prime factorization is given. Then we have to derive the following. There are two parts. This is part A, where we have to prove sigma of n times phi of n is greater than or equal to this product, n squared times this product of the factors of the form 1 minus 1 over pi square. We start the solution by recalling something. From exercise 8 of section 6.1, we know this. Sigma of n divided by n equals the sum of the reciprocals of all positive divisors of n. Now next you notice this. Now if we write the following product, this product where each factor is of the form 1 plus 1 divided by pi as a sum. How do you write it as a sum? You multiply out the terms. Then each such term will be of the form 1 divided by e, where e is the positive integer dividing n. Because it will be 1 divided by some product of those pi's, and the pi's already divide n. So this just means that each term in that sum is present here in this sum, and that is why this sum, which we know is sigma of n divided by n, is greater than or equal to this product or that sum. This product after all is a sum, or in other words, if you multiply both sides by n, you get this inequality. Sigma of n is greater than or equal to n times this. And then what you do, finally you recall the formula for phi of n, which is this. If the factorization of n is given like that in terms of the pi's, so you combine the inequality with this phi of n. Combine means you multiply, and that gives you your inequality. And next we have part B, where we have to prove that tau of n times phi of n is greater than or equal to n. We start the solution like this. We assume without loss of generality that each exponent ki is a positive integer. This we can of course assume. Then we consider tau of n, which we already know is this. It is equal to this. We recall the formula for tau of n from back then when we discussed this for the first time. So then, if each ki is a positive integer, then each ki is at least 1. So that makes each ki plus 1 at least 2. So here you are looking at the product of r copies of 2. So this is equal to 2 to the power r. So we find that tau of n is at least 2 to the power r. And now from exercise 7b, that means exercise 7 part B of this section itself, you get this inequality. Phi of n is greater than or equal to n divided by 2 to the power r. Just now you have established that tau of n is greater than or equal to 2 to the power r. So you multiply that inequality with this one, and that gives you your desired inequality.